Hello, everyone. These are not quite the circumstances under which I expected to be in this auditorium. Rohini's passing is even though her health was not great for a long time, and we all knew that, it is still quite unexpected. But it's good to be able to see everyone again. I'm going to talk about my PhD work, basically, which I did with Rohini, and also Professor Anuradha Mishra and her PhD students. So I think in yesterday's talk, Professor Mishra covered things very broadly, and today I will talk about two specific things. But before beginning, I wanted to say that I joined Rohini as I joined in the integrated PhD program in 2011, and initially I was thinking of doing particle physics, or I was thinking whether to go ask Professor Chandra Jog or Bani Bratha whether I could join them as their student. But I took a course in quantum mechanics too by Rohini, and her excitement was infectious, and I changed my mind and I asked her if she had a position open, and she did. So in this talk, it's basically, this talk is going to be about probes of the gluon-Sivers function, and the gluon-Sivers function is a transverse momentum dependent parton distribution function. So I'm going to briefly explain what a transverse momentum dependent PDF means in the next slide. So we are all familiar with this parton model picture of factorization of hadronic cross sections. You have a hadron electron or a hadron cross section. You can it has been shown that you can factorize the cross section into probabilities into a partonic hard scattering cross section, and probabilities essentially of finding a particular parton of a particular flavor inside a hadron. These probabilities are effectively PDFs, at least at leading order. And in the traditional factorization, which is known as collinear factorization, the partons are described mainly by the fraction x, the momentum fraction of the proton that they carry. So they are essentially quantities related to the structure of hadrons, and they have to be obtained from fits to data. They're non-perturbative quantities. While they cannot be calculated using perturbative QCD, PQCD does describe their Q-square evolutions. And the partonic cross sections themselves are perturbatively calculable, except when in most situations. When it comes to collinear factorization, only the longitudinal momentum fraction is relevant. The PDF is a function of the fraction x and a scale describing the process. So this factorization has been formally established for observables where the transverse momenta of the partons inside the hadrons are not relevant, which is true in many cases. But there are certain situations in which some processes are sensitive to the partonic transverse momenta. This could be, for example, in lepton pair production in Drellian in the small pt region. Unless the Drellian pair is recoiling against a gluon jet, or one or more gluon jets, its PT will be small, and it will naturally be sensitive. The PT of the Drellian pair will naturally be sensitive to the PT, the transverse momenta of the partons participating in the process. So a typical requirement for where TMD factorization is necessary is when there are two scales, a very large scale Q and a small scale associated with transverse momentum. And this Q, for instance, here is the invariant mass of the Drellian pair, and the PT would be the transverse momentum of the Drellian pair. So factorization in terms of such transverse momentum dependent PDFs. So here, because we are sensitive to the PT of the parton, we can establish a factorization theorem in terms of the which not only which involves PDFs which not only depend on x but also the partonic transverse momentum. So this has been established for simple processes. But TMD factorization is still not a fully mature field. Many aspects of it are in a state of flux. Unlike in collinear factorization, the Q-square evolution is not completely perturbative. There are non-perturbative aspects. And also, I think there was a slide in Professor Mishra's talk yesterday where she described various spin-dependent TMDs. So in the case of an unpolarized proton, you only have the collinear PDF describing the chance of finding an unpolarized parton inside an unpolarized proton. When you have when the proton has a spin, it can be either longitudinal or transverse with respect to the beam. You can have various TMDs, like 6 or 7 TMDs, but one of these TMDs is T-odd in nature, and it gives rise to these T-odd observables, which are called single spin asymmetries, and that's the Sivers function. And Rohini was particularly interested in the gluon Sivers function. So briefly, the Sivers function is a TMD. It describes the anisotropy in the KT space distribution of an unpolarized proton inside a transversely polarized nucleon. And it's basically due to a spin-orbit coupling effect. And the reason we care about the gluon Sivers function specifically is because, again, it's a spin-orbit coupling effect, which means that it has some information about the orbital angular momentum of the gluons inside the proton. And so you have the well-known EMC result, the proton spin crisis, in which the EMC collaboration measured the helicity data and found that only 1/8 of the spin of the proton is carried by the quark spin. And naively, you would expect that it would add to 1/2. And later data also showed that gluon helicity also contributes negligibly to the spin half of the proton. So large contributions should be coming from the orbital angular momentum. And so studying this will give some insights into the proton spin puzzle. So single spin asymmetries, very briefly put, because I might run short on time, are basically left-right distribution asymmetries, left and right with respect to the polarization of the proton. So here you have a polarized proton indicated by A, and its polarization is transverse with respect to the beam axis. And it can collide with an electron or another proton or a nucleus, and there is a asymmetry in the left-right distribution of the final state particle that you want to observe. Non-zero single spin asymmetries have been observed in many processes over a wide range of energies. So while Sidis and Relyan, these are the processes for which TMD factorization has been rigorously established. They are sensitive. In such processes, single spin asymmetries arise from quark Sivers functions, which are reasonably well known and well constrained. But the C quark Sivers functions are less well known, and the gluon Sivers function is very poorly constrained. But some Italian physicists did do some indirect measurements based on pi-zero production data at mid-rapidity at the relativistic heavy ion collider. So this is a process where quarks and gluons contribute, and they knew the quark Sivers function measurements from Sidis processes at Compass and some other experiments, and they extracted the gluon Sivers function. So this is in some sense an indirect gluon Sivers function extraction, and they give these two fits based on two different assumptions. Okay. And they both show a rather small gluon Sivers function, but with very different x dependencies. Sidis 2 fit, has a much stronger low x behavior than the Sidis 1 fit. So the question arises: how do you get access directly to the gluon Sivers function? Rohini in the 80s used to work with, I think, Luke and Rhea of the GRV PDFs on basically heavy flavor production, and she knew that, like, basically if you want good enough access to the gluon, you really go look at heavy flavor production, Charmonia, Dimaisons, and so she was one of the first people to suggest that, especially in the electron proton case, why don't you look at JPSI production, and that would be a very good probe of the gluon Sivers function. And so I think Professor Mishra talked about some of the first works, and I will talk about these two processes. All, the commonality is that they involved either heavy flavor production or direct photon production, which is also sensitive to the gluon through the Compton scattering process. So with JPSI production, this is something that can be observed at RIC. You have a proton coming in, which is transversely polarized, another unpolarized proton, and they fuse to form the JPSI, and we treated the formation of the JPSI with the color evaporation model, because a more sophisticated treatment is not required at this stage. And basically, you have an asymmetry. So the asymmetry has a numerator and denominator, and the numerator is proportional to the gluon Sivers function. And basically, the rapidity and the QT of the JPSI gives direct access to the gluon X distribution and the transverse momentum distribution with this setup. And I don't want to go into too many details of the parameterization of the TMDs, but basically we model the TMDs as a collinear part, which is based on the well-known fitted collinear PDFs. And we added a factorized transverse momentum dependence. In the unpolarized case, this is a Gaussian, and in the gluon Sivers case, we have a slightly more complicated form, and also allow for the X dependence to be modified with some parameters that we can set. So the Phoenix experiment actually measured the single spin asymmetry in JPSI production at mid-rapidity at RIC. And so what we did was we obtained predictions based on the SIDIS-1 and SIDIS-2 fits by the Italian collaboration, and also some other models by Bohr and Vogelsang, which are also well motivated, but I don't quite remember the reasons why they are well motivated. But it's been a long while. So Phoenix measured JPSI via its decay to muon pairs in the forward region, in mid-rapidity, and in the backward region. And we compared these predictions based on these models with Phoenix data after correcting for detector acceptances and taking into account that the JPSI decays into two muons. So basically, the disappointing thing is that Phoenix data is kind of compatible with 0, but with large errors. And the SIDIS 1 and 2 fits also give very small asymmetries. But the BV models give slightly larger asymmetries. So SIDIS 1 and SIDIS 2 fits agree with the data, but with huge errors, and this process cannot discriminate between the two fits. But the BV models are also consistent with the data, but they show slightly larger asymmetries. So the question is, can Phoenix distinguish between the two data motivated fits? And at that point, there was a proposal for a forward upgrade of the Phoenix. It was known as FS Phoenix. It was proposed to expand the forward coverage of the detector up to rapidity 4, pseudo rapidity 4. I think that plan was dropped, but we made predictions for that proposal, and we found that once you observe things in the forward region, where generally asymmetries are higher, given we could actually integrate over a large rapidity region, and we were able to potentially we showed that there is enough there will be enough cumulative data. It's possible to collect it to distinguish these two models. So basically, if the Phoenix upgrade goes through, they should be able to take enough data to distinguish between these two models. And second process was basically observing the Sivers function through gluon Sivers function through direct photon production. And so this is basically the process of gluon and a quark going to a photon and another quark. This is direct photon production is dominated by a gluon initiated process. And you can get rid of the fragmentation photon contribution by applying an isolation cone. And this is a brief plot in which we assumed maximal possible values for the gluon Sivers function as associated as allowed by, what is called a positivity bound, but basically by requiring that the PDF probabilities make sense. And we found that with you generally wanted to look at the backward region. By the backward region, I mean the region backwards of the polarized proton, and you can have pretty large asymmetries with a sufficiently large enough gluon Sivers function. But there is one subtlety here. So far, we've basically assumed that all the TMDs are universal, but transverse momentum dependent PDFs are in fact not universal. And this is because in the operator definition of TMDs, you need Wilson lines to make them gauge invariant. And these Wilson lines tend to be process dependent. And this is actually a well-known result. I mean, basically, and these Wilson lines basically take into account the interaction of the struck quark with the color field of the remnant of the target in case of Sivers, or it would be the interaction of the initial state quark with the polarized proton, the initial state quark with the color field of the unpolarized proton in Relian. So basically, in Relian and Sivers, the quark Sivers function has an opposite sign. And so we basically took these effects into account. And once you take these effects into account, it turns out that there are two independent gluon Sivers functions, and called the F type and D type. The F because you need an FABC in the operator definition, and the D type because you contract the gluon and DCs with the DABC. And we found that basically the F and D type Sivers functions contribute with opposite sign. The F type Sivers function has strong constraints from the quark Sivers functions, and that make it rather small in reality. But the D type is not constrained by any such rules, so it could potentially lead to asymmetries of up to 4%, which we need to measure. So to sum up, at present, all of the information of the gluon Sivers function is dependent on quark Sivers functions fits, so in that sense it's indirect. So we need to look at heavy flavored probes, which will give direct access to the gluons. The processes that we considered are all able to discriminate between the available fits and models for planned luminosities, and hopefully, I don't know about after at LHC, but EIC has been approved in BNL, and it should be able to give us very good insight into these distributions. So